Hello guys. Good morning. Good morning to all of you. Let me know if everything is all right. Good morning. Audio, video, everything is all right? Or is there any issue? Tell me. Good morning. Audio, video, everything is all right? Or is there any issue? Audio always remains an issue. But I think today is good. Is there any issue with the audio? Tell me, Harry. After a long time, we are taking live sessions again, and we'll keep on taking live sessions in future. Good morning, Murli. Is all okay? Everything is good? Can you start? So this will be an introductory class to our quantum mechanics course. So previously we have already taken quantum mechanics, but we took it in Hindi language. So therefore, because this batch was originally in English language, so we have decided to take those subjects which we have already taken in Hindi, will now be taking in English, and this subject course will be a detailed course. Previously it was a part of top 100 most important topics course, and those were also sufficient, like they covered almost 70 to 80% of the whole syllabus. Now this will almost cover the 100% syllabus. So let us start with the syllabus. What is there in your syllabus from the CSIR-NET physical sciences exam? You see, it has two parts. One part is the core part, another part is the advanced part, right? And you can see in the core part, it starts with wave particle duality. But before starting this wave particle duality, we need to know about the limitations of quantum mechanics. Some phenomena like blackbody radiation, photoelectric effect, Compton effect, and many other phenomena are there. You should learn before directly jump into the wave particle duality. After that, the main quantum mechanics starts with Schrodinger equation. So two types of Schrodinger equation, time dependent and time independent. Both will be equally useful. Most of the time, this time independent will be more used. After that, eigenvalue problems. Here we will have particle in a box. There are various types of box: symmetric, finite potential box, infinite potential box, asymmetric potential box, and many other boxes. Some step potential is also there. Then harmonic oscillator. So very important topic. We'll be talking about tunneling through a barrier, and in this part many things are included. You'll be given different types of potential. It may be some Dirac delta potential or some other new kind of potential will be given, and you have to plug in those potential in the Schrodinger equation and you have to solve. Okay, the solution will be the wave function psi. So mainly you will be given v of x, you will plug it into the Schrodinger equation, then you will be getting psi as the solution, and many times you will be asked to find out the eigenvalues. Then wave function in different representation, it may be coordinate representation or momentum representation. Then we will be going into the mathematical tools. Actually, before or after wave particle duality, we will be going for the mathematical tool in quantum mechanics, because otherwise you will not be able to understand the other things. Mathematical tools in quantum mechanics is very necessary. Once we are done with that, we will go for that other topics. Then Heisenberg uncertainty principle, this will be covered before. Okay, Dirac notation of state vectors, this is part of the mathematical tools. So look, this syllabus is given a little bit randomly, but we'll be going in a systematic way, and we'll make sure that all the topics mentioned in the syllabus is covered. Okay, because this comes under the mathematical tools, but they have given it later. Anyways, motion in a central potential, orbital angular momentum algebra, spin and addition of angular momentum. So mainly angular momentum you can say. Then hydrogen atom problem is there. It will take 2-3 lectures maybe. Stern-Gerlach experiment to confirm the existence of a spin. Then perturbation theory and applications. Now this will take a lot of time. Time independent perturbation theory and application. Most of the question comes from this variational method. Time dependent perturbation theory question may be set in the part C from this time dependent perturbation. This is we can say easier than the time independent part, because in time independent part several types of questions may be framed, but in the time dependent part there are few set of things which you need to learn, and once you learn them you will be able to solve questions. Then Fermi's golden rule and selection rules, but this is little bit difficult topic. So if you understand the topics before, you will be easily able to understand this time dependent part as well. Then we will have identical particles, Pauli's exclusion principle, spin statistics, connection. So these are very simple topics, so you don't need to worry about that. So this is the core part. Now if you go to the advanced part, you will see it has spin orbit coupling, finite structure, WQB approximation. So from WQB approximation, you know, previously it used to come one question from this particular topic, WQB approximation, scattering, Born approximation. One question, one or two question used to come before. Now also it questions come from the WQB approximation. Elementary theory of scattering, phase shift, partial waves, Born approximation. Then finally we will be going for the relativistic quantum mechanics. Okay, and with that, and classical theory of radiation will be covering, and with that our quantum mechanics course will be over. Okay, so in today's class we will be doing very basic thing. We will be introducing like what are the limitations of quantum mechanics. So classical mechanics, we used to deal with various classical mechanics problems. Okay, the mechanics which you see in our day-to-day life, a car is moving, a bike is moving, train is moving, and all those things. A ball, you throw a ball, and everything you discuss or describe by the help of classical mechanics. Now what is the requirement of quantum mechanics? So let us start with that. If anyone has any question or suggestion, you can let me know. We are starting our session. From the syllabus, is there any confusion? You can give me constant feedback so that I can incorporate it. Okay, if there is no question, let us start. Where classical physics failed? So you know, classical physics mainly failed in two domains. One is relativistic domain, another one is microscopic domain. So when the speed of any object close to the velocity of light, okay, when the speed of any object becomes approximately equals to or getting close to c, it may be 0.7 c, 0.8 c or so, then the usual classical mechanics could not or cannot give accurate result. Einstein's 1905 theory of relativity showed that the validity of Newtonian mechanics is at very high speed. So this is one domain. And microscopic domain, when you go very into the very small quantum region, okay, as soon as new experimental techniques were developed to the point of proving atomic and subatomic structure, the classical theory fails. Semi-classical theory was taken up, and later everything was discussed with the help of quantum mechanics. Okay, so these two domains, relativistic domain and microscopic domain, these were the two regions where classical physics could not provide reasonable explanation to various phenomena. Now what we know, if we have, let's say, a radiation, means we can say it is a wave like thing. So we don't expect, classically we don't expect that it will also have some particle like nature. For an example, if you have if you know about the photoelectric effect, we see that when some light incident on the metal surface, and if the incident energy is sufficiently high to eject an electron, what we see, we are sending, let's say, a wave, and what we are getting a particle. So how is this possible that we are sending a wave which is interacting with the particle and the particle is coming out? So from this we can say that this wave has some particle aspect. So that is the particle aspect of radiation. So if we consider, let's say, a particle, classical particle, how do you characterize a classical particle? What we need, a particle is characterized by an energy E and momentum P. Okay, energy is a scalar quantity, so we need vector quantity to get it more accurately. Momentum, so if you know the information of momentum, you can get the idea of what may be the effective mass and velocity product, and as it is a vector quantity, you will also get the direction, so you will get a complete information. So to represent a particle, we need this energy or momentum, and if you are considering a wave, what you require like what is the amplitude of this wave and what is the, let's say, wavelength. Okay, and you also need to know in which direction this wave is propagating. So we need a wave vector. Wave vector is represented by K. Okay, this is wave vector. Try to understand the basic difference between the wave vector and wave number. The magnitude of wave vector is known as the wave number. Okay, this is known as wave number. Okay, so particle and waves exhibit entirely different behaviors. Particle, you know, and what behavior they show, and wave behaves differently. Classically, we cannot like correlate between those two, but from this kind of experiment we see there may be some correlation between the wave and particle aspect, and this is later given by the wave particle duality by de Broglie. Okay, so this concept was very rigid. Like the rigid concepts of classical physics were not sufficient to describe the microscopic phenomena like blackbody radiation, photoelectric effect, and Compton effect. Mainly for these three phenomena, blackbody radiation, photoelectric effect, and Compton effect, the classical explanation could not provide any reasonable description. So we need to take up the quantum mechanical approach to describe this microscopic phenomena. Okay, so we will be discussing these three one by one. Today we will keep our discussion limited to this blackbody radiation, then we will be going for photoelectric effect and later quantum effect, Compton effect. Okay, so let us start with blackbody radiation. Now many questions came previously from this particular topic, and this is a mutual topic between we can say quantum mechanics, thermodynamics, so that is why this is very important. Now look, this theory, this part of the lecture is mainly theory. Okay, and I will share the PDF, don't worry, in the course folder, so you just focus on it, and if you have any question you can ask me instantly. So what is blackbody? Blackbody is an idealized physical body that absorbs all the incident electromagnetic radiation. Whatever radiation incidents, it will absorb, regardless of frequency or angle of incidence. And you know, this blackbody is a perfect absorber. Perfect absorber means whatever radiation falls on it, it will absorb, and at the same time it will emit all type of radiation. All type of radiation means radiation of all frequency. That is why, so when you consider the emission, okay, emission spectrum, and if you plot it, you will get all type of frequency. Means you see, if I consider this as a frequency and this is maybe intensity, so it will start from 0, nu will start from 0, and it will contain all kind of frequency, means 0 to infinity, all the type of frequency will be included in the black body radiation spectrum. But because we are human, we can only perceive the visible portion of this spectrum. Visible portion may be 370 nanometer to 700 nanometer. So only this part we can observe with our bare eyes or naked eyes. Other portion of the spectrum we cannot observe. Okay, just a moment. Now any black body, if you consider, it will remain in a thermal equilibrium. Thermal equilibrium means it will maintain a constant temperature T. So it will emit all kind of electromagnetic radiation, EM radiation, and this radiation is known as the black body radiation. So whenever any object is heated, it radiates electromagnetic energy as the result of thermal agitation of electron on its surface. The intensity of radiation depends on its frequency and the temperature. Okay, so when you write the intensity, we will be writing in terms of nu and T. It is a function of frequency and temperature. Sometimes we also write it in terms of the energy density. We write U nu of T, or more frequently we will be using this U nu D nu. Okay, so sometimes we will be plotting intensity versus frequency, or this energy density versus frequency, intensity versus wavelength. Okay, so both of these curves are useful equally. Intensity versus, let's say, frequency, intensity versus wavelength, and all those curves. So later, actually, there is a inverse relation between nu and lambda. Okay, nu is equals to C by lambda, means nu is proportional to 1 upon lambda. So whatever will be the form here of this black body radiation curve, it will be changed a little bit slightly. It will be just reciprocal of that. Okay, an object in thermal equilibrium with its surrounding radiates as much energy as it absorbs. So a black body radiator is a perfect absorber as well as perfect emitter of radiation. So this part you need to keep in mind, that black body radiation is a perfect absorber as well as a perfect emitter. So these are very basic things. You should be able to understand it very carefully, very clearly. Now if you look at the black body radiation curve, you see what we have plotted. We have plotted intensity versus frequency. So as I told you, intensity is a function of frequency and temperature, and as a result of that, you see, depending on the temperature, let's say temperature T is equals to 5000 Kelvin here, temperature T equals to 4000 Kelvin here, temperature T equals to 3000 Kelvin, and here it is 2000 Kelvin. So as we keep on changing the temperature, the intensity pattern got changed. Okay, so for a particular temperature, if you vary the frequency, you will get a single curve. Now at other temperature, if you vary the intensity with frequency, you get another curve. Now just notice carefully one thing, that in all the curve there is a peak. Okay, so for this, the peak lies here. At T equals to 4000 Kelvin, the peak shifts towards left. Okay, for the frequency. So obviously when you plot it with wavelength, this peak shifting will be in the opposite direction. Here you can see, as you keep on decreasing the temperature, the peak of this curve is coming towards the left in the intensity versus frequency curve. In the intensity versus wavelength curve, this situation will be just reverse. As you keep on decreasing the temperature, this peak will shift towards right. Okay, as you can see, this peak with respect to frequency, it is shifting towards right upon the decrease of temperature. Okay, upon decreasing temperature, the peak is shifting towards left. Clear? And this relation is mathematically given by Wien's displacement law. So you can see this is the spectral intensity distribution of black body radiation at different temperature as a function of frequency. So what are our observation. I have already told you most of the observation, but here I have just put forward it. Look, at a fixed temperature T, any temperature T, the intensity of the blackbody radiation increases with frequency. As you can see, this is increasing with frequency, achieving a maxima, and this falling down again. New max, and then decreases at a higher frequency. This is described by Planck's radiation law. This plot is being governed by Planck's radiation law. Before the advent of Planck's radiation law, there are some other law like Rayleigh-Jeans law, Wien's distribution law. So those law were specific for particular region. Maybe for low frequency region, some model was accurate. For some model, the high frequency region was suitable. But there was no model which can explain the total blackbody radiation curve, total experimentally observed blackbody radiation curve. Only the Planck's radiation law fits the experimental result perfectly. And you know the Planck's radiation law, you should remember this formula, U of nu T. This is the energy density at a particular frequency and particular temperature. It is given by 8 pi h nu cube by c cube into 1 by e to the power h nu by kt minus 1. So this expression will be requiring in when we will be covering the laser Einstein's AB coefficient, then also this will come. Good morning, Ajay. How are you? Now you see, as the temperature increases, the emitted frequency spectrum becomes broader. If you have observed this, you can see previously, you can see this was a little bit sharp. Now as you decrease the temperature, it has got flattened. It has got more flattened. So you see, the curve becomes broader and broader as you keep on decreasing the temperature. Oh, sorry. Temperature, when you are increasing the temperature, it is getting broader now. Oh, I just told the reverse thing. You see, this curve is obviously broader now. So it is finishing here. So very limited region, but you see, that is why it was not matching, but it's okay. As you keep on increasing the temperature, to 2000, 3000, 4000, 5000, so it is getting broader. Okay. Now this third point will be talking separately also. With increasing temperature, Wien's displacement law indicates that the frequency of the maximum radiation shifts to higher frequency. So you see, as you increase the temperature, the frequency peak shifts towards right. Okay. So if we take it like this, the peak shifts towards right. When you increase temperature, and when you decrease it, shifts towards left in the intensity versus frequency curve. So be very careful what you are plotting. Either you are plotting intensity versus frequency or intensity versus wavelength, because for the wavelength it will just be reversed. Okay. If you are decreasing T, the peak will shift towards right in the intensity versus wavelength, and for this it will shift towards left. It will just become opposite. Now you see, this part of the emission curve is important, because this comes under the visible portion. This is the visible portion. Visible portion, this to this, and this portion we use in calculating many things. Let's say we are at the Earth's surface, right? We are at the Earth's surface. Earth is becoming. We are at the Earth's surface. Now we are getting constantly electromagnetic radiation. So maybe from a distant star or somewhere we get some electromagnetic radiation we receive. Okay. Now from the electromagnetic radiation we can calculate and we can plot this curve, and from that, without measuring the temperature, we can get the temperature, because you see, in all the radiation curve, the maximum point gives you an idea about the temperature, right? So if you study this spectrum, whatever spectrum we are getting from a distant star, we can plot it, and from that peak we can estimate the temperature of that body. So we can get the temperature of different astronomical object using the blackbody radiation curve. That is why it is very important. Okay. So visible we can do with our naked eyes, but for infrared and all we need extra setup. Now Wien's displacement law we have already told you, but let's put it in a better way. Wien's displacement law, it states that the wavelength lambda max we have talked about in terms of nu max. Okay, now frequency is being maximum means lambda will also be maximum at certain point. Okay, so lambda max corresponding to the maximum intensity of the blackbody radiation is inversely proportional to the temperature. So you have to remember this formula: lambda max into T is equals to constant B. This constant has a value, this is known as Wien's constant. It has a value 2.898 into 10 to the minus 3. This is not a millikelvin, this is meter Kelvin. You see, lambda has the unit meter, T has the unit Kelvin, so that is why this is meter Kelvin, not millikelvin. This is meter Kelvin. And as you can see here, T1, T3 is greater than T2 is greater than T1. T3 greater than T2 greater than T1. So as you come down, the temperature is increasing, and as a result of that, you see the peak shifts towards right. So with increasing temperature in the intensity versus wavelength, the peak shifts towards right. We can see this law implies that an increase in the temperature of the blackbody radiation causes a blue shift in its emitted radiation. Now you see two terms are there, blue shift and red shift. You know, from the Vibgyor formula, Vibgyor, you know, this red color has the maximum wavelength, max wavelength. Okay, and here you see blue is not minimum, it's low wavelength, lower. So blue shift means it is going towards blue, means wavelength is decreasing. If it is a right shift means it is going towards the red shift. Sorry, right shift, no, red shift. So when the wavelength is increasing, it shows that red shift. Look, this is a simple fact, but don't get confused whether it will shift towards right or left. Just focus on this formula. Okay, let's say you have a curve. Now lambda into T, lambda max into T, it is constant. If it is constant, you see, to keep it constant, if you increase the temperature, obviously this lambda max will decrease, right? So once you increase the temperature, this lambda max will decrease, and if you decrease the temperature, lambda max will increase. and this is the line of lambda. Maybe there may be some problem with this curve. Okay, if it is T3, T3 is the maximum temperature, means lambda should be minimum. As you can see, this lambda is minimum. Then moderate, then temperature is less, so wavelength is increased. Temperature is further less, so wavelength is further increased. So you just remember this one, then this red shift and blue shift will not create any problem. In both cases, upon increasing temperature, here it in increasing temperature, the peak shift towards right, and here upon increasing temperature, the peak shifts towards left. Actually, you see, there is a confusion, but I think it is correct. You see, you are increasing temperature from this side now, T1, T2, then T3. So you are increasing temperature from this. So peak is shifting towards left. Now I think it is clear, Karthik. Actually, I gave this sign opposite. Now I think it is fine. As you are going from down to up, you are increasing the temperature. So peak is shifting towards left. And here you see in the frequency it is opposite. You are increasing the temperature, peak is shifting towards right. Is it clear now? Everything is all clear now? Either you go, so don't remember in this way, this in terms of blue shift or red shift, it will confuse you. You just stick to this. Okay, you may be given two curves at least to compare. So you will see whether T is increasing or decreasing. If T is increasing, lambda max will decrease, means it will come towards this. If T is, let's say, decreasing, means lambda max will increase, means it will go to this, because this is 0. So lambda is increasing along this side and lambda is decreasing along this side. So I think you are smart enough to incorporate this. Will you be able to handle this? Any question? Now an application, very important application, is the star temperature. So using this method, we can estimate the temperature on the star surface. Stars, approximately blackbody radiators. Their visible color depends on the temperature of the radiator. The curve shows blue, white and red star. Blue, white and red stars. The white star is adjusted to 5270 Kelvin, so that the peak of the blackbody radiation curve is at the peak wavelength of the sun, 550 nanometer. So this temperature, you see, we have lambda max into T is equals to B, and we know the value of this B, 2.898 into 10 to the power minus 3 meter Kelvin. Okay, now we have, from the distant star, we get the blackbody radiation curve, right? It is emitting the electromagnetic radiation because it is behaving like a black body. So it will constantly emit electromagnetic radiation. Now these distant stars are like maybe millions years away from us. So let's say one electromagnetic radiation is emitted maybe hundreds years back. Now when you are receiving it on the earth, you are getting it 100 years later, and whatever you are receiving, you are plotting it in this blackbody radiation curve, and from this curve, from the maximum portion, maximum value, you can get the lambda max value. And once you get the lambda max, because you know that this product is always constant and this has this numerical value, so T you can get by putting this B by lambda max you will get from this curve. So you can exactly calculate the temperature of the star surface. Okay, what is the quantity in y axis and is it energy density? Yeah, yes, E at lambda means energy at lambda. You see, energy density means what? Energy per unit volume. So let's say U nu d nu, right? So if you integrate the whole energy density, what you get? You get the total energy, na? So this is like the total energy, or let's call it simply intensity. Okay, intensity or U nu, U nu d nu can say. So it we are talking about lambda, so that is why I of lambda t actually. I of lambda t. Okay. What is intensity? Energy per unit area per unit time. This is what intensity is. So same thing. Don't worry about that. Just a little bit of multiplication factor is varied, otherwise same thing. Sometimes we represent power density, sometimes intensity. So we have the liberty to do that. Main important thing is this x-axis, whether we are plotting wavelength or frequency, that needs to be checked. Let us do this problem quickly. Estimate the wavelength of radiation emitted with maximum intensity by a glowing tungsten filament whose surface temperature is 3300 Kelvin. Can you do this quickly? So we can directly use Wien's displacement law. Look, Wien has two laws. One is this Wien's displacement law. You can predict it from the name. Displacement means this peak is getting displaced. Another one is Wien's distribution law, which we'll be talking about it later. Lambda max times T, this is 2.898 into 10 to the power minus 3 meter Kelvin. So from this we can get the value of lambda max, that is 2.898 into 10 to the power minus 3 divided by temperature is 3300 Kelvin. So this will give you around 878 nanometer. Okay. Now this is universal. Lambda max into T is this constant is universal. All the time you will be using this constant, fixed for all radiation system. C is coming out to be the answer. Okay, I think everybody could do this. Now, as I told you, the black-body radiation curve was previously tried to explain by various scientists. Okay, one of them was this Wien's. He gave his Wien's distribution law, but it failed. Wien's approximation, also sometimes called Wien's law or the Wien's distribution law. Wien's law or Wien's approximation or Wien's distribution law is for the spectrum of thermal radiation. This equation does accurately describe the short wavelength or higher frequency. Okay, high frequency. Remember this one. Wien's distribution law is applicable for high frequency. There is Rayleigh-Jean's law, but Rayleigh-Jean's law at high frequency gives rise to ultraviolet catastrophe. So Rayleigh-Jean's law does not describe the high frequency portion, it only describes the low frequency portion. To describe the high frequency portion, we need Wien's distribution law. Now you need to remember this mathematical form. Actually this directly follows from the Planck's radiation law. We'll be deriving that. You see, U of lambda d lambda. So this is energy density in terms of lambda, 8 pi hc by lambda to the power 5 e to the power minus hc by lambda kt d lambda. Remember this one. In terms of frequency, this relation you have got 8 pi h nu cube by c cube e to the power minus h nu by kt d. This is Wien's distribution law. This explains the higher frequency side. If you plot, let's say, I versus nu, so you'll be getting a curve like this. Okay, so high frequency means this portion of curve. This is described by Wien's distribution law. Now we'll be talking about Rayleigh-Jeans law. So Rayleigh-Jeans law fits well this low frequency side, but as you go on high frequency, it gives rise to this ultraviolet. It becomes infinity. It becomes ultraviolet catastrophe. Okay, this portion is described by Rayleigh-Jeans law. Rayleigh-Jeans law describes the low frequency side, right? Now Rayleigh-Jeans energy distribution, you see, it describes the longer wavelength, means low frequency side. However, it fails at shorter wavelength. Shorter wavelength means higher frequency, and as you consider higher frequency, it gives rise to ultraviolet catastrophe, leading to the ultraviolet catastrophe. This thing is important. Sometimes in interview also this ultraviolet catastrophe is asked. Very simple thing, not much difficult. You see, U lambda d lambda 8 pi kt by lambda to the power 4 d lambda, and the main problem is this. You see, in terms of frequency, it is U nu d nu is equals to 8 pi nu square kt by c cube d nu. So you can see this is proportional to nu square. Okay, now when you integrate this, so this frequency will keep on increasing. So at infinite frequency, you see, ideally this intensity becoming infinite. If nu becomes infinite, this U nu d nu integration over maybe 0 to infinity, this becomes also infinite, or it diverges. This thing is known as ultraviolet catastrophe, and this is represented by this straight peak here. So I have given you this form separately, ultraviolet catastrophe. You see, the ultraviolet catastrophe refers to the classical physics prediction that the energy density of the black body radiation should increase indefinitely at higher frequencies or short wavelength, and leading to an infinite total energy. Total energy, you see, if I consider U nu d nu, if you integrate, that gives you the total energy. Okay? If you integrate the energy density over the all frequency range, it gives you the total energy, right? This result was derived from the Rayleigh-Jeans law, which states this. So this is the energy density. You are integrating over all frequencies. All frequency means it will be covering from 0 to infinity, 0 to infinity. It is going up to infinity. So this term getting diverges. So this divergence at high frequency contradicted the experimental observation, which showed that the black body radiation has a finite energy distribution. This is the actual, no? This is your actual result, and as you can see, this is finite, not infinite. If you integrate this curve, it will give you a finite result. Integration means what? Area under the curve. That is the meaning of the integration, right? If you have the curve, this integration means area under the curve, and as you can clearly see, if you integrate, it should give you the finite result. But as per the Wien's Rayleigh-Jeans law, you are getting an infinite result. So that is why it is discarded. And later, black body radiation curve was given by Planck's radiation law. So here is a basically summary of what we have done till now. So intensity versus frequency, it is plotted. In the lower frequency side, it is described by Rayleigh-Jeans law. Lower frequency side is described by Rayleigh-Jeans law, you can say, and the higher frequency side is described by the Wien's distribution law. And the overall curve, experimentally observed curve, is described by the Planck's radiation law. Now let me tell you again that try to focus on this expression u lambda d lambda 8 pi kt by lambda to the power 4 d lambda. This is Rayleigh's law. And what about Wien's displacement distribution law? It is 8 pi hc by lambda to the power 5 e to the power minus hc by lambda kt d lambda. If you can remember these two forms, then it will be better for you. Why? It will be revealed in few minutes. You see, Planck's radiation law, this you must remember. It describes the spectral energy distribution of the electromagnetic radiation emitted by the black body in thermal equilibrium at given temperature T. So this gives you the intensity of radiation emitted from a black body which is kept at a constant temperature of T. It is given by 8 pi h nu cube by c cube 1 by e to the power h nu by kt minus 1, and in terms of wavelength it becomes 8 pi hc by lambda to the power 5 1 by e to the power hc by lambda kt minus 1. You know, I of nu t is the spectral radiance per unit frequency at temperature. So sometimes we write d nu, so it is we have omitted d nu, so that is why it is per unit frequency. And similarly for per unit wavelength and then frequency of radiation. So under appropriate approximation we can show that this Planck's radiation is approximated to Wien's distribution law, and under some approximation it also approximates the Rayleigh-Jeans law. Rayleigh-Jeans law. Now we'll show you how Planck's radiation law gets converted into those two basic laws. So first of all, we'll be trying to derive the Rayleigh-Jeans law from the Planck's radiation law. Okay. I hope everything is all clear till now. So we'll be discussing two cases. Case 1, let's say, on longer wavelength. What is the meaning of longer wavelength? Longer wavelength means smaller frequency side. What we have seen in the smaller frequency side, which law fits well? It is Rayleigh-Jeans law. Okay, so let's see. Longer wavelength means hc by lambda. In this formula you see e to the power hc by lambda kt. So hc by lambda, this part we are trying to take hc by lambda. If lambda is long, hc by lambda will be less, right? So we are comparing with kbt because it is hc by lambda kbt. So we want this factor. It means because lambda is long, so this is much less than kt. So hc by lambda kt, this becomes much less than 1. So very small number. So you know, if let's say x is a small, e to the power x we can approximate to 1 plus x, right? Like if let's say x is very small, then we can approximate that e to the power x is approximately 1 plus x. So using this analogy we can rewrite the Planck's radiation formula 8 pi hc by lambda to the power 5 d lambda e to the power hc by lambda kt minus 1. Now we can approximate this result. As we know, e to the power hc by lambda kt, you can write 1 plus x is hc by lambda kt, and this minus 1. So this plus 1 and minus 1 is getting cancelled. So what we are getting ultimately? Look, hc and hc is getting cancelled, so we are getting 8 pi kt 1 lambda is getting cancelled, 8 pi kt by lambda to the power 4 d lambda, and this is what? This is precisely the Rayleigh-Jeans law. So we started with Planck's radiation formula, and we are ending up at Rayleigh-Jeans law. So we can say that Planck's radiation law approximates the Rayleigh-Jeans law in the longer wavelength limit. So we can just write line, thus Planck's radiation law approximates the Rayleigh-Jeans law in the long wavelength limit, right? So this is the first case. Who did this experimentally observed first? Experimentally observed, everybody, that result experimentally was observed at first. No, or you take a black body, you study the spectrum and you saw that. Okay, so actually what happened? Initially scientists took the radiation, they got a curve like this. Okay, after this was experimental curve. Now the job of the scientist was to describe this curve. Why we are getting this curve? To explain this experimentally observed curve, first this Rayleigh-Jeans tried, but he only able to explain this part, the low frequency side, and his model did not fit the high frequency side. Once he tried, he could explain the high frequency side, but he could not explain the low frequency side. So there was no model which can explain the total experimental curve. Then finally in I think 1905 or something, this Planck's radiation law came, which exactly fits with this experimental curve. Okay, so this is what it is. Planck's radiation law came and it accurately fits this experimentally observed curve. Now what was special about Planck's radiation law and why this Rayleigh-Jeans law or Wien's distribution law could not explain? Because Planck's used the quantum mechanical idea. He used the quantum mechanical idea that the absorbed and emitted energy are quantized in nature. So when he incorporate this approximation, many approximations were there, I am just telling you a few, then it got fitted with the experimental. Now why the results of Rayleigh-Jeans or Wien could not explain? Because they relied on the classical physics, but Planck's used semi-classical physics, means he introduced quantum mechanics into his theory and he got the final result. So that is what we are discussing. This black body radiation, it could not be described in terms of classical physics. We require semi-classical physics with a quantum mechanical touch to describe the experimentally observed result. I hope this is clear. Let's go for the case 2. Case 2 on shorter wavelength side. Shorter wavelength means what? Longer frequency side. So when it is shorter, means hc by lambda. Lambda is small, so this term becomes greater. hc by lambda kt becomes much greater than 1. Now if you see that if x is very large, then e to the power x will be how much? E to the power x will be much greater than 1, we can say, because x is very large, so e to the exponential of that number will be very large, so it will be much greater than 1, and as a result of that we have u lambda d lambda 8 pi hc by lambda to the power 5 1 by e to the power hc by lambda kt minus 1. So this one is much greater than 1, means we can ignore that, this minus 1. So we can write approximately 8 pi hc by lambda to the power 5 e to the power minus hc by lambda kt d lambda. So we can conclude here that Planck's radiation law approximates to, and this is your Wien's distribution law, Wien's distribution law. In the short wavelength limit, in the short wavelength limit. I hope everything is all clear from this blackbody radiation. On the next class, we will be discussing the two other phenomena which could not be explained using the classical mechanical idea: photoelectric effect and Compton effect. Okay. Let me know if there are any question till now, or we are in a position to end the session. And every day we will be taking our class at 7:30. So join it. I can send the link at the previous time, in the night or in the morning also, but make sure to attend the session from 7:30 am. Every day, almost every day except Sunday. Okay. Thank you guys. Thank you very much. If you don't have any question, we are stopping the session here. Thank you. Bye bye. Take care. Yes, Karthik. Ask anything you want to ask, you can ask. And you can also ask your doubts in the live class. You are asking, that is good. In addition to that, you can also ask via DM on WhatsApp. Okay, whenever I will get time, I will try to explain. For descriptive type of exams in physics, can you suggest any tips? Are you descriptive type? What kind of descriptive type question you are? In which exam you are appearing? Is it in the geophysics exam or in some other exam, or in your state PSC exams? Can you mention any name of the exams? Oh, descriptive type. So that is a good thing actually. Look, the best approach for the descriptive type question is, whatever previous year question you have, you just cover them first. Okay. Otherwise, yes, I now understand what you are talking about. Assistant professor recruitment. Yes. So if there are any previous year questions which are there, you can practice those first questions first. Okay. That is one thing. Now in your state, some state PSCs are there, administrative service. So they also have a physics main paper, right? Physics mains. So that is descriptive, na? state PCS. So solve those PYQs first. You see what kind of question they are asking. Let's say you take a topic, you take a question paper, and you see what kind of question is set. Obviously, whatever we have studied here for Planck's radiation law, they will not ask so much mathematical thing. They will simply ask you like derive Planck's radiation law, or they can ask you in this way, what are the basic assumptions in Planck's radiation formula? Write the formula and derive it. It's this kind of thing question. This kind of question may be asked. So best approach would be from the multiple PYQs, you just take up question topic wise. Set a topic and see what kind of question came. So note them down, and from that you will get an idea what kind of question may be set in future. And based on that general finding, you can prepare your notes. Notes making is very important for descriptive type question. So prepare notes and try to practice. Keep a daily maybe 1 hour time, 1 or 2 hours of time to write. You have to write, otherwise you will not be put forward your answer in the final exam. So give a fixed amount of timing to practice writing. That will help you. This is the first time they are conducting descriptive type exams for assistant professor. Yes, in UP also, for the GDC exam, General Degree College exam on assistant professor, they have decided to take it on the descriptive mode. Actually, descriptive mode is good in one way and bad in other way, because when you are cracking CSIR-NET, you are already doing the new MCQ questions. Okay, so they, I think because the eligibility criteria gives equally all the net qualified students the opportunity to sit for the exam. So that is why they are changing maybe the exam pattern, so that only the knowledgeable persons get to sit into the examination. Because you see, what is the basic motivation in introducing the descriptive questions? You see, there are many students who take coaching maybe for 6 months or 1 year. So they just only follow the short notes, maybe the final formula. They don't have the idea what is going on behind. So to tackle that, this kind of descriptive questions is necessary. Okay, I always encourage you that okay, for cracking CSIR-NET, formula revision is important, but try to understand what is going behind. Okay, whenever you get time, but don't compromise with the preparation, because this time your ultimate motive is to crack CSIR-NET JRF. Okay, but for being assistant professor, you have to like know about the things in a more detailed way. You can call me sometimes, we can discuss about it more. Let's end the session here, and if you have any question query, you can let me know via DM also. Bye bye, take care, have a great day. And everybody like the video, okay?